All right. Thanks everybody for coming. I don't know, it's probably because this is a new batch of papers, more so than people are excited to read Paxos, but still I'm appreciative that everybody's coming. All right, so it should be a fun discussion. I think the Paxos stuff is pretty interesting and pretty, I don't know, insightful. So if you took a look at the paper, the abstract and the intro admittedly comes across a little aggressive. We're like, oh, we have low throughput and low latency, and we're simpler, and we're optimal. I wouldn't view the paper so much like that. That was sort of just a bit of paper engineering. I like to view this stuff as there's this class of generalized consensus protocols, like Paxos and Caesar. I think Balaji's the author on that. And what was the other one? Atlas, which we read in this group like a while back. And Paxos or Bipartisan Paxos is just trying to say, can we understand all of these protocols a little better? Because these protocols are a little complicated, and for good reason. So Paxos is going to try to say, can we understand these more complicated protocols step by step? So I'm not going to be able to have time to go through every single detail, but I'm going to at least hopefully have enough time to present the basic stuff. And I hope that if you have this sort of basic understanding the other protocols becomes a lot easier. Okay. So let's get started. First, I'm going to start off with a quick refresher of Multipaxos. Okay, we thankfully don't have to understand all the details of Multipaxos and understand this talk. But with Multipaxos, I'm going to have, let's say, F+1 proposers. One of the proposers is going to be elected the leader, so I'll draw with a crown. I'm going to have two F+1 acceptors. And I'm going to draw these guys in a box. I'm going to draw these guys in a box too. And we're going to have F+1 replicas. And if I'm some client and I want to propose some state machine command X, I will send the command X to the leader. The leader is going to choose some log entry in which to place X. Let's say here it's log entry 0. It's going to send a phase 2, blah, blah, blah. I'm not going to go over the details, but it'll send essentially X and 0 over to the acceptors. The acceptors will vote for it, send it back to the leader, and then the leader will notify the replicas. And every one of these replicas has its own version of the log. Every log entry has some index, and it'll say, okay, X got chosen in the log. They'll execute these logs in prefix order, and then they'll send back a response to the client. Okay, so we go client to proposers to some set of nodes which accept something, back to the proposers, and then you notify the replicas. Okay, so we're going to see that Paxos follows something, it looks very similar, but there's going to be a couple of differences. The first difference involves the log. So let's consider the following Multipaxos log. Oops. So in Multipaxos, every replica has a totally ordered log. And every replica has to execute every command in this log in the same order. So let's say I have the commands set A to B, set A to 2, set B to 1, set B to A, and set A to 2. And these are in log entry 0, 1, 2, 3, 4, and so on. So in Multipaxos, every single replica has to execute this sequence of commands in exactly this order. They all execute A + B, then they all execute A + 2, and so on. But what would happen if I were to swap the set B to 1 and the set A to 2 commands? So let me say set B to 1 and then set A to 2. So if one replica does A + B, sets A to B, sets A to 2, sets B to 1, sets B to A, sets A to 2, and another replica sets A to B, then sets B to 1, then sets A to 2, then sets B to A, then sets A to 2, does it matter at all? It shouldn't matter. The two executions are completely indistinguishable. And that's because A = 2 and B = 1, they commute. Or I could say they don't conflict.
So can I have a question here?
Yeah, what's up, Faisal?
Yeah, so are we here assuming that there are no atomic reads that we want to apply to the copies? Because, for example, if I want to do a read of A and B, So we're either getting the state of 0 and 1 or 0 or 2. So even if we're doing a read of A and B, it wouldn't matter, right?
Yeah, great question. For this talk and in the paper, let's ignore reads. Let's say if you're going to do a read, you have to get it chosen in the log. Yeah, so we're not going to do any clever optimizations to do reads. And if we do those optimizations, you're right. I think that some of these things get a little more complicated. But for now, let's just ignore the fancy reads. That's a good question. Okay. So the idea here is that if I have two commands that don't conflict, aka they commute, aka I can execute them in either order and I get the same final state and all the intermediate states are the same, then it doesn't really actually matter what order I execute them in. Okay, so in Bpaxos, as well as ePaxos and all these other protocols, we're going to not use a log. We're going to say, forget the log, throw out the log. Who needs a log? Instead, we're going to decide on a graph. So the graph is going to look something like this. Oh, well, it could look something like this. It could look like something else too. But let's say we have A equals B, B equals, or let me do A equals 2, B equals 1, B equals A equals 2. And we'll have some edges in here. Okay, so we said forget the graph, or sorry, forget the log. We're going to go to the graph. And this graph is going to have these properties, which I'll explain in more depth later. But for example, two commands are going to have an edge between them if they conflict. And I'm also going to label each vertex with a little number, just like we do with a log. And with a log, I execute things in prefix order. So I execute the first command and the second command and the third command and so on. With the log, or sorry, with the graph, I'm going to execute the log. I feel like I say the wrong thing more than half the time. With the graph, I'm going to execute the graph in reverse topological order, one strongly connected component at a time, which sounds very fancy, but here, for example, it would be, okay, this is a component, and it's the first one, so I have to execute this. Then I can execute command 1 and command 2 in any order. And then these final guys are in one component. I have to execute that last. And when I execute nodes within a component, I have to make sure to do it in some deterministic order. It doesn't matter which, so long as we all agree. So here, to make that more concrete, when I execute these commands, I'm either going to execute command 0, then 1, then 2, then 3 and 4. Let's say within a component I execute in increasing ID order. Or I'll execute 0, then 2, then 1, then 3, then 4. Because I can execute 1 or 2 in either order, these are both valid topological sorts of the graph. Okay, any questions so far on that? On just the idea of forget the log, we're going to go with the graph. Instead of doing log order, we're going to go prefix order or topological order.
I have one question, Michael.
Yeah.
So this graph looks like a cyclic graph, and we do topological sort only on DAGs, like B equal to A and A equal to 2. There might be cycles in the graph.
Yeah.
So how do we handle those?
Yeah, great question. So yeah, right here, for example, very astute, we have a cycle. So when I do this topological sort, I'm going to do it one component at a time. So if I ever have a bunch of nodes which are all connected, you can imagine it's like I'm collapsing that to a single node, and then I'm doing the topological sort.
Okay.
Yeah. That's a good question. And we'll see later why we even have cycles and sort of what those cycles mean. But that's a good point. The cycle is not an accident. That's important. We'll see later. Any other questions? Okay. So I want to really quickly drive home the point of the differences between multi-Paxos logs and bipartisan Paxos graphs. With multi-Paxos logs, I have a bunch of boxes, and every box has some number, 0, 1, 2, 3, 4, 5, and so on. And with multi-Paxos, I'm going to choose the log one box at a time. First, I run consensus on the first box, then the second box, then the third box. So let's say I choose A equals B in the first box. Well, this is a prefix of the graph, so I can execute it. Let me underline in green the ones that I execute. Then let's say I choose A equals 2. Well, I can execute that. Then let's say I execute, I choose, sorry, A equals 1. Whoop, that's not right. That should say B equals 1, right? Oh, well, doesn't matter. I execute that. And then let's say I get A equals 2 chosen over here. Well, I can't execute it because there's a hole in log 3. right? So I'm only executing stuff in prefix order. And also note that there's a hole in the graph, right? That doesn't seem weird at all to us, hopefully. That's sort of normal. We're going to see in graphs, we're also going to have holes, but it becomes a little more strange. Okay, so if we're going to look at this in the graph, I'm also going to be choosing things one box at a time, except now it's going to be a vertex and all the edges out of that vertex. So let's say I choose A equals B as before. I'm going to call this vertex vertex 0, and it has no outgoing edges, so I can execute it. Then let's say I choose A equals 2 with log entry 1, and it has an edge to A equals B, but I've already chosen A equals B and executed it, so I'm free to execute A equals 2. Then let's say I choose B equals 1 with an edge to this guy, and this ID is 2. Well, B equals 1 only depends on things which are chosen and executed, so I can execute this. Now the weird part, let's say I get A equals 2 chosen in slot 4, and this thing has edges to the first command, but it also has an edge to this box, which is empty. So with the log, this doesn't seem weird to people. The log can have holes. But with graphs, we're going to see the same thing. I can have an edge to a vertex, and that vertex can be empty. I can choose A equals 2 with an edge to another box, which has nothing chosen in it yet. So here I won't execute A equals 2, but later, let's say that I finally choose, what is this command? B equals 4. When this guy finally gets chosen with whatever edges it has, maybe it has a cycle, now I can execute both of these nodes. Okay. Any questions so far on that? I haven't explained how I choose these graphs or like any of that, but just in terms of if I were to give you a graph, would it make sense how I execute it?
This might be like a basic question, but why are there holes in the logs? I mean, that I didn't get that.
Yes, it's not clear why there are holes. That will become clear.
Okay.
Yeah. Faisal, you had something?
So yeah, I think I think what's coming, but with the thing, just to give us an intuition. So are these graphs chosen by the proposers or by who? And also, is there a corresponding log instance of each graph that the proposer are aware of, or is it only the graph?
Yeah, great question. So we're going to see here in a second that in the same way that Multipaxos chooses one log entry at a time, Bpaxos is going to choose one vertex at a time. So just like with Multipaxos, I go to a proposer, the proposer takes something, puts it in a log entry, and then gets it chosen. With Bpaxos, a command will go to the proposer, it's going to choose a vertex, it's going to figure out the dependencies, the edges somehow, and then it's going to contact the acceptors and get that thing chosen and then notify the replicas.
Yeah, so it's that somehow that I'm still not getting, but maybe now you're going to get into it.
Exactly, yeah. So once we know what the graphs sort of look like and we understand abstractly that things will get chosen one at a time, now we're going to jump into, okay, more concretely though, how do we go about choosing all these things? Before I jump into that, are there any more questions just about the graph itself? Okay. All right, yes, perfect. Yeah, every time I give this talk to a smart audience, everybody is always very eager to get to the actual protocol, which I think is awesome. Okay, so Bpaxos overview. I'm going to give a high-level overview of the protocol first, and then I'm going to dive into each component in more detail. So I'm not going to explain every single detail right now, but I'm going to give you a high-level overview of the flow of the protocol. And it's going to look similar to this original drawing. I drew this Multipaxos picture at the top in a very particular way because it's going to reflect Bpaxos. Okay, so as before, I'm going to have f+1 proposers. I'll just call them proposers. And one of these proposers, no, actually, one difference is I don't have a leader anymore. So neither of these guys, well, maybe I'll draw both with a crown. I guess that's a matter of perspective if they all have crowns or none of them have crowns. I'm going to have, well, actually, I don't want to say that. I'm going to have some abstract box that I call consensus. And this box, this black box is going to implement consensus, but I'm not going to tell you how yet. I'm going to have some other black box, which I won't tell you about yet, called the dependency service. Dependency service. And I'm going to have f+1 replicas as before. Okay. When some client, maybe I'll do a landscape to make this a little bigger. When some client has some command X that it wants to get chosen, it's going to send X to any of these guys now. There's not just one leader, it's going to send it to any of the leaders. With Multipaxos now, the leader is going to put X into some log entry. Here it's the same thing, except the log entry index numbers are going to be a little more abstract. We can talk about that more later. But it's still going to choose to put X into some vertex labeled I sub X. So in these graphs up here, these things are like the I sub X's. If this thing has X in it, this would be I sub X. All right, so think of it like a log number. It's just an ID. All right, so it's going to say, okay, I want to put X in a vertex called I sub X. And then it's going to send it, then it's going to send it to the dependency service. The dependency service is going to compute a set of dependencies, which are just the outbound edges, and send them back. So it'll send back, okay, I got your X, IX, and I computed depths of IX. And if we look at that graphically, that would look like some vertex with a command X in it, labeled IX, and it has edges to some other boxes. And these boxes together is depths of IX. Depths of IX. For example, depths of IX could be the set IY, IZ. Oops, IZ. So the dependencies is just a set of other vertex IDs. Okay? So client sends X to any of the leaders. The leader puts X in a box called IX, sends it to this dependency service. Dependency service sends back and says, okay, here are the dependencies you should use. And at this point, the leader is going to send to the consensus service. It says, hey, I want to choose X, depths X, depths IX rather, in an instance called I sub X. So this consensus service is implementing one instance of consensus per vertex IB. So just like with Multipaxos, I have one round of, like I have one instance of Paxos for log entry 0, one for log entry 1, one for log entry 2. Here I have one instance of consensus for vertex called IX, one for IY, one for IZ, and so on. This thing is going to choose the command once and for all. That's what consensus does. And it'll send back that it's chosen. Or maybe something else was chosen and there's some dueling stuff, whatever, but it chooses something. And at this point, the leader is going to let all the replicas know. Every single replica, if we were to zoom in, is going to maintain its own view of the log, and it'll have something that looks like this now. It'll have an I sub X with an X in it with edges to whatever the depths were. Okay. Any questions on that high level bit? We only have 15 minutes left. Okay. I'm actually, no questions actually. Let's try to dive into the details of these guys now. Okay, so first, first I need to show you two key invariants. Two key invariants. Invariant 1 is I implement consensus. Okay, invariant 2 is for any pair of commands, X and Y, that conflict, chosen with depths IX and depths IY, then either IX is in the depths of IY or IY is in the depths of IX, or both. Okay, this sounds very complicated, but all it's saying is, assume I have two boxes, one with X, one with Y. One of them is called IX, the other one is called IY. If these two commands conflict, then I better have an edge either from X to Y or from Y to X or both. And this is just the intuition we had before. It doesn't matter what order I execute things if they don't conflict, but if they do conflict, then there better be some edge between them. Okay. So I showed you these two black boxes up here, consensus and the dependency service. Now let me dive deep into how to implement them. Okay, so let's talk about implementing consensus. Okay. Use Paxos. That's it. So one of the nice things about this protocol is we're sort of modularizing a bunch of stuff. And because of that, I don't have to go through and prove anything. If I want to show that I satisfy invariant 1 and I implement consensus, it's trivial. I'm just going to use Paxos. So that black box, I'm just going to throw Paxos at it. Or if you have some other protocol you prefer, maybe you want to use like vertical Paxos, go for it. It doesn't really matter. Okay. The second is implementing the dependency service, and this one's a little more interesting. Implementing the dep service. Okay. And remember that the key invariant here we're going to have to maintain is the second one, that if two things conflict, they have an edge between them. Okay, so I'm going to implement the dependency service with two f+1 dependency service nodes. Dep service nodes. And every one of these dependency service nodes, let's take a look at it more carefully, is going to maintain a graph. So let's say a proposer sends the command x in instance ix to one of these dependency service nodes. What it's going to do is it's going to make a box called ix and put x in it, and then it's going to add edges from this box to every other box it has that conflicts with it. Here there are no other boxes, so there are no conflicts. So it's going to send back the empty set. It's going to say, I have no other boxes I conflict with. I have no dependencies. Then let's say it gets y in instance iy. And let's assume that y conflicts with x. It's going to put y in a box called iy, and it's going to say, oh, hey, y conflicts with x, so I'm going to draw an edge from y to x, which means it's going to return the set ix. Then let's say it receives z in the instance iz. And let's say z conflicts with both x and y. Well, it's going to make a box, it's going to call it z, it's going to put iz, it's going to draw an edge from y to y and to x, and then it's going to say, oh, okay, my dependencies were iy and ix. Okay, so dependency service nodes, they maintain their own little graph. All they do is when I get a command, I just put it in the graph and I draw edges to everything else that I conflict with. If I get the same command twice, I don't have to add it twice. Okay, so that's each individual dependency service node. But how does the dependency service act as a whole? Well, if these are the dep service nodes, and this is some leader, when it receives a command x, it's going to send x, ix, to all of the dependency service nodes. And it's going to wait to hear a response from at least the majority. So maybe the middle guy crashes or something. But only f will crash. I'll always have f+1. I'll always have a majority. And when I get a response from a majority, maybe the first guy on the left here responds with iz, and the second guy responds with iy, I'm going to take the union of those. So deps ix is going to be the union of these two things, which is going to be iz, iy. All right, so I send x, ix to all the dependency service nodes. When a dependency service node gets x, ix, it's going to add a box called ix with x inside of it to its local graph. It's going to draw edges to everything else it conflicts with and send back those conflicts. I'm going to wait to hear back from at least f+1 of the dependency service nodes, and I'm just going to take the union of all of the dependencies. Any questions on how that works before I prove why that's correct? No, okay. So this dependency service has to maintain invariant 2. It has to be that if two commands get chosen and those commands conflict, there better be an edge between them. Well, thankfully the proof is actually quite simple. Let's consider the two f+1 dependency service nodes. And let's say that x is chosen with some set of f+1, because the proposer is going to contact f+1. And y is chosen with some other f+1. Well, the thing about any two majorities is they intersect, which means that there will be some dependency service node, at least one, there could be many, that has seen both x and y. So this guy has seen x and y. And the idea is that whichever it saw second will have a dependency on the first. So if it sees x then y, when it gets y, it'll have a dependency to x. If it sees y then x, when it gets x, it'll see a dependency to y. Which means that when the proposer takes the union of all these dependencies, it will definitely see the other one. Faisal, you have a question?
Yes. So is it only the order? So is it possible that two operations would be ordered differently in two nodes?
Yes, great question. And that is exactly why at the very beginning, our graph can have cycles. So our graph will have a cycle precisely when two different dependency service nodes sees two commands in opposite orders. So maybe one sees XY and one sees YX, then that means that both of these commands are going to have an edge from one to another. If every dependency service node happens to see every command in the same order, which is not required and most likely will not happen, then we don't have any cycles. It's because that they can see them in either order that the cycles happen, but it's not a problem. Did that answer the question?
Yeah, but can't this get really complicated when it's more than two operations?
Complicated in the sense of like the graphs get really nasty.
Yeah.
Yeah, the graphs can get nasty for sure.
I think it's going to get clearer when you tell us how you deal with these cycles.
Yeah, so the cycles, so you should hopefully already be equipped to know how to do the cycles. So when I get a graph of cycles, I'm still just going to execute it in reverse topological order.
Oh, I see. I see.
Yeah, I don't actually have to do anything to resolve the cycles in terms of like, I don't have to go do some fancy recovery. Cycles are fine. I just execute them in reverse topological order. Yeah, so cycles are not to be feared. They might slow things down a little bit, but they're not really this big scary thing. Okay, let's see. I have 7 minutes. Okay, I will give a quick little mini summary here. Okay, so to recap, I have 2 proposers, 2 replicas, 3 dependency service nodes, and probably 3 acceptors. The client is going to send X. I'm going to put X inside some box called IX. I'm going to wait to get dependencies from at least the majority of the dependency service nodes. I'm going to take a union of them. Then I'm going to send X, IX, and deps IX to consensus. I'm going to say, hey, can you please choose this thing for me? It'll say, yeah, sure. I get it back. I send it to the replicas. These replicas are going to add a little thing to their graph with maybe some edges. Maybe I have a cycle or something, but that's okay. And then they're going to respond to the client, and they're just executing these graphs in reverse topological order, just like normal Multipaxos replicas execute their logs in prefix order. Whenever they get something, they add it, they check to see if they can execute something, they execute it. Okay. I have 6 minutes. Let me talk about recovery real quick. So it is possible, oh, I can even reuse this drawing. It is possible that some replica has a command X in a box called IX that has an edge to some other box, IY, that has nothing chosen in it. And maybe the proposer that was trying to get something chosen in IY crashed and it's forever not going to get anything chosen. Well, then I'm kind of stuck. It's the same as I don't want a hole in my log in Multipaxos forever. I don't want an empty box in my graph forever. Thankfully, this is actually very easy to solve. If I am some replica, let's say this replica, and I notice that I have a vertex called IY with a hole in it, I'm just going to contact the dependency service and say, hey, can you choose a no-op with no dependencies as vertex? And it'll either, maybe it'll say, oh, actually some other thing was already chosen, you just don't know about it, or it'll choose this, and then I'll get a no-op chosen in IY, and it'll have no edges out of it, and then I can execute X. So recovery is just go to consensus and choose a no-op. Okay, I have 4 minutes left. I probably won't have time to dive into the next part. So how about I take questions for the next little bit, and then if there's not questions, I can briefly summarize the next part.
Hey, Michael.
Yeah.
How do you collapse the roles? Because you have all this, different roles and all these message exchanges. That's a lot of like communication going on. How do you collapse it down so that it's actually fast?
Yes, great question. Okay, I'm jumping in. Assume I had written this all. This was my practice version of the talk. So the next thing I would have talked about if I had time is how do I reduce the latency of things and how do I collapse all the nodes, right? I have all these different nodes. I have a bunch of different network delays. How do I reduce that? The idea is that I am going to co-locate the dependency service nodes with the acceptors. I'm going to co-locate the proposers with the replicas. And instead of using Paxos, I'm going to use fast Paxos. And now when a proposer sends a command to a dependency service node, that node computes the dependencies, and instead of sending it back to the proposer, it's going to propose it in a fast Paxos instance to the co-located acceptor. And then that acceptor is going to return its vote to the leader. And if it happens to be that all of them agree, well, if a fast quorum of them agree, F plus whatever, F plus 1 over 2 plus 1 or whatever, then we've reached fast Paxos consensus on a set of dependencies computed by the dependency service node, which means I don't have to do an extra round trip. Okay, so I'm sort of collapsing in the dependency computation and the consensus all in one by using fast Paxos. But then the thing is, and this is the fundamental thing, I wish I had time to talk about this. This is like the most interesting part. This is actually wrong. And it's wrong because there's this very fundamental tension when we start using the dependency service and consensus. And this tension is like the core part of all of these protocols. Because, I think I have it written down here, fundamental tension. The thing is, consensus is saying, hey, go choose something. And if something was maybe chosen before, you better choose it. I don't know if it was chosen, but if anything was maybe chosen, you have to choose it. But the dependency service is saying, no, 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 no. You can't just choose anything. The dependencies that you're choosing have to be computed from a majority of the dependency service nodes. If my dependencies are computed from one node, then my dependencies maybe don't have these conflict edges. So you have this tension. Consensus is saying, you better choose this. And the dependency service is saying, no, 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 don't choose that unless you're really confident it's safe. And resolving that tension between the two services is the fundamentally hard thing that these protocols have to do. And there's different ways that you can go about resolving the tension. So for example, I mean, this won't make really much sense. Hopefully you can read the paper, but if I increase my fast Paxos quorum sizes, then I actually solve the tension in a really nice way. And Atlas actually is doing this. It's not very obvious that Atlas is doing this. If you don't want to compromise quorum sizes and you want to keep them small, then you have to get really complicated, and protocols like Caesar and ePaxos start to get down this more complex path of how do I keep my quorum sizes small and still navigate this tension? Okay, I have to go in 1 minute. Any final 1 minute length questions?
How do you identify conflicting transactions? I did not get it.
Yeah, great question. So we sort of just assume that away. We just say assume you have some mechanism. In practice, it depends on whatever your state machine is. For example, if you have a key value store with only single key operations, identifying conflicts, you would probably just maintain like a hash table from the key to the all operations on that key. If you have more complicated operations, you have to do more complicated things. Okay, I'm going to end the recording. Stop.